Okay, you can see my screen.
Yes, sir.
Okay, so let's see. So we saw so far in SMT logic, so as a predicate logic with types that you saw that recap. After that, you were there for the demo also. So that.
Yeah, sir. The one that Digant did, right? Yeah.
Okay, so how comfortable you are? I mean, have you had a logic course? No, that.
Yeah. I've had a logic course.
You have had. So you are. I mean, the other two have not. Okay.
Yeah, I have already had
So a
logic.
little bit more, comfortable. Okay.
Yeah.
So, but here's what an SMT solver from a black box perspective is. So you have these formulas, first order formulas, built out of atomic formulas, which are kind of, you can use any Boolean combinations. Okay. This is the quantifier free fragment I'm restricting myself to for the time being. Okay. So, but in first order knowledge, you can also have quantifiers. But for now, let's say you have a quantifier free. So you have then, if it's quantifier free fragment that you are considering, then what the formulas are any Boolean combinations built from atomic formulas, which are drawn from various theories. Okay. So these atomic formulas will be built using the predicate symbols or equality, which we normally assume as that exists over terms, and the terms are the ones that are that belong to the various types of theories. Okay, various sorts, and the each of them is assumed to be, each of those sorts or types are assumed to be governed. The non-logical symbols belonging to that are governed by some. I mean, they're constrained by a set of axioms. Okay, so that's how. So this is how it is, and so what does we will get? So. Okay, that's first order logic. So these are the theories. Okay. So for example, this could be theories involving arrays. This is bit vectors. Okay, where greater than is shift operations. This, but one here, 2x plus y less than or equal to 5, can be drawn from the standard arithmetic theory, which could be the real, integer or natural numbers. And x is equal to gy is some theory that we will talk about, which has equalities and some function symbols. These function symbols can be uninterpreted in the sense that they don't, they can be denoting any functions that you want. And then, so that's what is the input, some Boolean combinations of any one of these kinds of things. And then what you really do is either you check the satisfiability or unsatisfiability of these kinds of formulas that are constructed. Now, I've just shown you a little bit of what the overall top-level architecture of an SMT solver is. Usually there is a core solver, there's something called DPLL, which takes care of the Boolean part of it. And then, for each of these theories, there is a separate solver. Okay, for example, if it's a linear inequality over a real arithmetic, then SMT solver could be using an LP solver, so based on either a simplex algorithm or whatever, or anything else, and it talks to the So it has various theory solvers. These are solvers that check the satisfiability for conjunction of formulas. Okay, conjunction of atomic formulas. And the DPLLT and the core solvers. The core solvers used to combine these the checking of conjunctive atomic formulas drawn from various theories. And DPLL takes care of the arbitrary Boolean combinations with which these things can be constructed. So we'll be talking a little bit more about that as we move along in the course. But today what I want to do is, so this is what I already said. So, okay, so this atomic formula could be as equality and some function symbols. This is the theory that I want to illustrate today, okay, and to illustrate how that can actually be used for modeling and verifying DNN as an illustration purpose. After that, I will introduce program, the application of logic for program verification. Okay, some basic points. So here is the theory of equality, a formal of theory of equality. So whenever you introduce a theory, what is the first thing you will have to do? You will have to define the signature for it, which consists of all the function symbols, and the function symbols and predicate symbols that belong to that theory. So here it has just one predicate, which is equality. Okay, and it can have some variables x, y, and z, and so on. And these function symbols, f, g, and it can have some predicate symbols also. And these predicate symbols and function symbols, they are all assumed to be uninterpreted. Okay, what does it mean? So what are the axioms it has? It has the axioms which define the meaning of equality. Okay, so here we say the equality symbol is assumed to satisfy reflexivity, symmetry, okay, symmetry and transitivity axioms. Okay, so in any model in which you check this has to obey all these, have to satisfy all these axioms. Okay, and that's how you present theory. Additionally, so nothing is assumed about the function symbols in this theory except the congruence property of the function symbols. Okay, because this is the standard. If f is a function, then all it says is that if you apply to equal, arguments that are equal as per the equality symbols, then the result of applying f on, if the corresponding arguments are equal, then the result of applying this to x1 through xn should be equal to f applied to y1 to yn. Okay, that is if the argument are pairwise, corresponding arguments are equal, and the same thing for all the predicate symbols as well. Except for these things, this thing does not assume anything else. These are the only basic properties about the thing. So given this, then you can have, for example, formulas of this kind that you can draw and then check the, what was that? There for the intro.
Yes, sir.
Huh?
What did you ask again? Could you repeat?
No. I was just going to give you an example. Okay.
Okay.
I'll use this example. There was an example that I had in the intro thing, for example. I don't think I have. Well, I mean, it can have things like like this. Before I get to this particular example, so let me use this. So, for example, if you have okay, so for example, this one is an example that belongs to this theory of equality with where it has a single function symbol. Now, as per is this true? Is this valid? I mean, is this valid, or let me take this, okay, not equal, say, okay, is this satisfiable in this theory? As per, huh? Yeah.
It shouldn't be, right?
It is not satisfiable, right? Because why? Because fx is equal to x. If fx is equal to x, as per this congruence axiom here, okay, as per congruence axiom, you have so it violates. Okay, so you have f of x is equal to fx. Okay, for example, yeah. And that's what this. So you could. So if you an SMT solver, can easily take care of these kinds of things, or combinations of various much more complicated things. It can check the unsatisfiability of these things. Yeah. Okay. So, and if your problem is such that interesting things from that, your real artifact is conducive, is amenable to this thing, then you can do it. So that's what I'm using an example, considering another more interesting example here. This is something in the introduction lecture that I already given. So let me revisit that. So here is showing, checking the program equivalence, okay? So roughly, even before we talk about how you model program using logic, etc., which I will get to later in the thing. So here, this computes, its output is expressed in this way, okay? Through a series of assignments, okay? So it says assigns y to z, x to y, x to z, and then computes x times x, okay? It's just a convoluted way, but it's here it does in a more direct fashion, okay? As you can see, in this case, regardless of what star is, just by equal, it doesn't matter what star, the function star is actually the interpretation for star, okay? It could be multiplication, or it could be anything, okay? So just by using the theory of equality and function symbols, you can leave star as uninterpreted, okay? And still, this will be not satisfiable. You have to have R2 to be equal to R1, correct? Through just equality propagation, you can actually check this, yeah? So here it does not depend on the meaning that you attach for star, at all. Therefore, so you could use this theory theory of equality with uninterpreted function symbols. So while this program equivalence is meant to work on bit vectors, if you give a special interpretation for the bit vectors, of course, you can reduce this to a Boolean satisfiability problem. Okay, I mean, assuming that these are bit vectors, then you can encode all the multiplication, etc., as bit vector operations, and finite size bit vectors can always be operations of finite size bit vectors can always be encoded as a Boolean bitwise Boolean formulas. Correct? Okay, so you could use a SAT solver, which only does I think that is one way to do, or use an SMT solver, which is more, using the theory of equality and uninterpreted function symbols. Since in this case, this is the satisfiability or the unsatisfiability of here is independent of the interpretation, specific interpretation that you give to star, you could use an SMT solver with a theory of equality and function symbols. And then, while a SAT solver takes 5 minutes, using this theory of equality, it does in a fraction of a second. Okay? So, so I'm just giving you an example. So there I'm just replacing star with mul, where mult is is uninterpreted, then I can use this, and therefore if it works for any function, obviously it has to work for any uninterpreted function. For any specific interpretation, it has to work. Okay, so that is kind of, I'm illustrating the use or the power of an SMT solver. In some cases, it can be even better than SAT solver, if the problem fits. So yes, okay. So I guess I'm making 2 points. I hope thing. So for this problem, just theory of equality with uninterpreted function symbols, the one that I've shown, is good enough. Okay, to solve, because it doesn't matter what the domain actually is. Okay. Okay. So as another example, let me move to now talking about this one. I guess in your demo, okay, so generally, okay, so this is what I'll switch gears here. So using logic for formal verification of real life artifacts, okay? So I'll come back to how, so how we could now use SMT logic and solvers for, doing this. And then the first example I'll use, okay, in general, when you use, the steps involved in using logic, in general, and particular SMT solvers, for checking, for doing formal verification or checking certain properties of real-time artifacts. And I call it real life artifacts, and they could be either, neural networks or programs. Those are the two things that I'll illustrate using by drawing examples from. In the course, you will be looking with special interest to how we can apply it to neural networks. So in general, you have 3 things you will have to do. One is you have to specify the expected behavior. What is it that you want to verify about the system? Okay, that need to be specified in logic. Okay, in predicate logic. then you have to model all possible relevant behaviors of the artifact, also as a formula in that logic. Okay. So we already saw how SAT solvers, SMT solvers could be used to model games. Okay, I mean some board games. Okay, that and some problems. Okay, so but here I'm illustrating it for some things like DNN and in particular programs. So the second step is in modeling all possible relevant behaviors of the artifact, okay, for all inputs, okay. Then the third thing is to reduce the verification problem into checking validity of a appropriately constructed verification condition. So just like when you used in the case of this 8 queens problem, there was this modeling part. You had to figure out what propositional variables to use in order to model the scenario, and then you had to construct a formula whose satisfiability, satisfying instance, satisfying instance was a solution. Similarly, in this application of formal verification, you will have to then construct an appropriate formula whose validity reduces to one of showing that the model of your program or your DNN indeed meets the specification as specified. So these are the 3 components that you will have to. These are the 3 tasks that you will have to do. Okay, in general. So let's take. And what I want to do in today's class is to illustrate this in the case of DNN and for programs. Okay. So this particular example, I guess Diganta already used in his class to the demo purpose. Did he?
Yes, sir.
Okay. But anyway, I will go through it again. Okay. So that maybe the way that I model might be slightly different in the way that he did, but I want to really see I want you to see the connection. Okay, the theory of equality with uninterpreted function symbols. I'm going to use that particular the SMT logic with that theory in order to perform these 3 steps. Okay, for in verifying it. That is the one. That is the analogy, and that is the connection that I want you to see in this illustration. Okay. So first of all, here, what are the theories that you will have to that you will need? So I'm saying that I can do it using what I need is, because these inputs are assumed to be reals. Okay, what you're getting are real numbers, and therefore you need the standard theory of reals. Okay, which in mathematics is represented by Z. So I'm going to have to use the theory of reals. Okay, so where with all its standard operations with standard meaning. Okay, and then I'm going to be using a theory of uninterpreted function symbols. Specifically, there is a ReLU function here. Okay. So in order to model that, I will have an additional function symbol. I mean, a function symbol which I consider as uninterpreted. Okay, and a function symbol called ReLU. Then I'll have variables, specifically variables here to denote the output at each of these nodes. Okay, either the input node or the output of all the other things. And finally, I also introduced a few variables to denote the because the operations that happens in each node here, internal node, there is a linear transformation that happens followed by ReLU application, correct? So I'm going to be using these variables F21, F22, F331 to denote the result of applying the linear transform at that function, at that node, at that particular node. Okay. Now, so that's the theory that I'm going to be using, and now I'm going to be expressing the modeling. That is the I'm going to show you how I'll model as a formula. Okay, from this in first order logic over these theories, the result, I mean the behaviors, all possible behaviors for all possible inputs of this particular DNA. Okay, so this has, and by this formula, this has, this is the one that I'm using. So I use phi DNN to denote that formula. It has basically three parts. One is, it says, it defines F21, F22, the linear transform that is happening at each of the internal nodes and the output node. Okay, so F21 is equal to V11. F22 is -1 times V11, and that's what I'm saying here. And I'm sorry, this should be F31. F31, not 33, is V21 plus V22. Okay, where V21 and V22 are the output of this node after the ReLU application. Okay.
Excuse me, sir. Shouldn't it be F31 is equal to F21 plus F22? Or
no, because I'm assuming V21, V22 to be the output of the node. Okay, and you see at each node there are two operations that happens. There is this linear transformation of the input, okay, followed by a ReLU application. Okay, so so that's, I'm splitting that into two parts here. Okay.
Yeah, got it.
Yeah. So V21, whereas F21 and F22 are just the linear transformations, okay, because there is a ReLU application, okay, which is what I'm defining here, okay. So ReLU is technically an uninterpreted function symbols, but here I'm saying, but ReLU here, when applied to Vij, when applied to Fij, which is what will be set to, Vij will be equated to, and this is done for 2, 2, and 3, 1. So here I'm defining through these equalities the values, the values denoted by the variables V21, V22, and V31, which is the result of applying the ReLU function. So here I'm saying Vij is ReLU of Fij, okay, for each of those indices. And the constraint on ReLU itself I'm specifying here, okay? So if Vij, I'm sorry, this should be Fij, okay? Once again, I made a mistake, okay? Read this. This thing should be Fij, okay? If Fij is greater than 0, then ReLU of Fij is equal to Fij, okay? Sorry, so there are several mistakes here. So I apologize for that. So this Vij, this all should be Fijs here. No, all Vijs, read it as Fij, okay? So if Fij is greater than 0, ReLU of Fij is Fij. If Fij is less than or equal to 0, then ReLU of Fij is equal to 0. So these are the constraints on ReLU, because I'm letting ReLU to be an arbitrary function, but with this constraint is what I'm saying. So So given all these things, so then a conjunction of all these things is, it kind of models, you can say it models the behavior in the following sense, because it defines what V31 is for an arbitrary value of V11. Okay, so this is modeling the behavior, all possible behavior, that is all possible for all possible inputs in the following sense, that any instances of V11 and V31 and all the other variables, any satisfying instance of this formula happens to be a valid input output of this DNA. Is that clear?
Yes, sir.
Yeah. So in that sense, I'm saying it is modeling all possible behaviors. By all possible behavior, I mean the outputs for all possible outputs produced by the DNN for all possible inputs. Okay. And that's what that is one of the steps of formal verification. Now, what is the specification that I want? What I really want to prove is that it's actually a universally quantified formula for all V11, V31 must be equal to, that this should be valid is what we should check. This is what I call as the specification. Okay, what I want to check about this system, which is now modeled as logic. That also should be expressed as a formula in that logic. Okay, that is the second one. Then you have to now construct a formula whose validity check. I mean, you have to reduce the verification problem. You really want to verify that for all possible, this specification, that for all possible inputs V11, the output produced by the DNN, which is V31, is equal to the input. Now that really means that because phi, the formula denoted by phi DNN, it really represents that behavior. Okay, so it is really then the problem of verification, checking that the specification is indeed preserved, I mean satisfied by the DNN, reduces to checking the validity, that is, of this formula, this entire formula. Okay, that is for all. I mean here, when you check the validity, it means for all possible models, which implicitly means that for all possible. I mean for all implicitly when all these things are universally quantified. Okay, for all values of V11, V31, and of course there are the formula has other variables which are all defined in terms of your input variables and the various function symbols. Okay, that functional terms that belong to the theory. Okay, so then it is one of checking that this formula is valid, and this formula, as you know, is a first order formula in this the theory of equality over equality with uninterpreted function symbol, in which in this case has a single ReLU function. This is equivalent to checking the negation. So since validity checking can be reduced to checking unsatisfiability of the negated formula. So that's what I've done. So an implication corresponds to this junction of negation of the antecedent. This is like not of phi DNN or V3 is equal to V1. When you take the negation, it becomes phi of DNN and V3 and not of V31 equals V1. And so the checking the validity of that is checking the unsatisfiability of this one. Now this can be shipped off to an SMT solver, and using, by appropriately inputting these formulas into Z3, you can actually check this. And that's what I bet Diganta did in his demo, okay? I don't know if he used the same example, but if you were to use this example, that's what you would do, yeah? Any questions? Do you understand? I mean, do you have any questions or doubts?
No, I got it.
Yeah, but I'm kind of belaboring the point, okay? This connection that you will have to see, because depending upon the problem, you have to use these appropriate theories, okay? That is supported by the SMT. In this case, I'm using a combination of two theories. One is theory of reals, and the thing that why do I need theory of reals? Because after all, say I'm using various operations on reals. This negation plus, okay? And in this case, I mean, generally, if the coefficients are something other than 1, you'll also need multiplication, okay? All those are defined by the theory of reals, okay? In this case, in particular, we have theory of linear inequalities over terms of reals and the ReLU function, which and plus equality. Okay, so as you can see, yeah. So this is the combination that I'm using. So now, if you have no questions, I will now illustrate the same thing for doing verifying some properties about programs. Okay, so for DNN, this was kind of fairly simple, because after all, what was going on was there was a linear transformation which could easily be expressed as an expression in the theory of reals. And the ReLU is where I'm using the theory of equality with uninterpreted functions. And then ReLU has an if then else kind of structure, which I'm then using the propositional logic, okay, for doing. So let's see. So the modeling part, when I want to illustrate in the next few slides how you could use it for program verification, okay? Okay, so can you give me just 30 seconds? I'll go grab some water to drink, yeah?
Yeah, sure.
Thank you. I'm back. So let's consider a very simple program, a straight line program, which has a sequence of 3 assignments. First, how do you specify this? So how do you specify a program? Okay, it could be various ways. Normally, you're interested in, as if you for certain assumptions about its inputs, you expect when you execute the program, the outputs to meet certain conditions, correct? So this is a simple swapping program, okay? So you could specify the program, the expected behavior that you want to check for a program by giving 2 formulas. One, a precondition, which denotes assumptions on the inputs as a formula. So once again here, since the variables are ranging over reals, I'm using the theory, the standard theory of reals, okay? And you will see all my properties that I care about can be specified in linear inequalities. Okay? So specifically, I'm using theory of linear inequalities. So if if I assume X is less than Y, after I execute this program, then the specification says, I expect this condition specified by this formula to be true, that Y should be less than X, because this program swaps the value of Y and X. Okay, so one way, very popular way of specifying expected behavior of a program is through this pre and post conditions. Okay, clear?
Yes.
Have you seen such specifications of program before?
No.
Okay, so this is called the pre and post conditions way of specifying the program. Okay, so now in order to reduce this problem of checking if this program, for all possible, the formal verification problem is defined as one, which is to verify this program for that it meets this specification for all possible behaviors of the program, which it means for all possible inputs, this should hold good. Okay, is what problem of formal verification is, and that we will do. The testing is one way to do where you simulate it. Okay, so here the idea in formal verification is to do it without actually running the program. Okay, by reducing it into a problem of checking validity of an appropriately constructed formula in first order logic. So for that, first you need to model the behavior of a program, just like you did in the case of DNN in the previous illustration. There are various ways, various methods to model behaviors of program. That is a very rich, field. At one point, it used to be a very popular research topic, called programming logics and so on. Here, I'm going to illustrate to you one way of doing it, which is very conducive to using SMT logic and SMT solvers. Okay, and this one is called, you're modeling through what is called static single assignment. Okay, it's called SSA. So here, what I do is, as you know, what happens when you execute a program? The values denoted by these variables, these program variables, change after every instruction, correct? Maya?
Yeah.
So what here you do is you kind of introduce logical variables to denote what the value of X is at each point, okay? At the beginning and after each assignment statement, okay? So in the beginning, there are some initial values, and these are denoted by these logical variables X0, Y0, and Z0. Okay, and now, then here's what I'm using. So I'll tell you what an SSA is. Okay, so this is what I'm constructing, an SSA. Okay, it just is here. Each of these formulas, everything that I denote within curly brackets is a formula in logic, as opposed to these things which are programming, constructs inside the programming language. Okay. So here is what is called static single assignment. That's actually a formula. Okay, what it says is it introduces a new timestamp variable to denote the value after execution of this instruction. Okay, so what it's saying is Z1, since this is assigns X to Z, so Z1 will be X0, and everything else remains unchanged. Okay, so Z1, X1, Y1, and Z1, they denote the value okay, of that are in the variables after this thing. Okay, and that's what and this static single assignment, because every time you're only changing one variable, that's why only one variable changes. All the rest will remain the same. Okay. You actually, in static single assignment, I'm showing that they're not changing explicitly here. You know, there is an optimization, okay, which I will refer to, but you know, so you don't need to keep things, so you can. But anyway, so let's think. So similarly, after x is equal to y, so denote this formula here, any satisfying instance of this formula exactly captures what the values for the variables are in terms of the values that existed prior to the execution of the statement, precisely what the values of the variables are after that statement is executed. Correct? Yes, Samayam? So any?
Yeah, good.
Yeah. So similarly, you do it here. Yeah. So after this, what you know, since this changes only x, so you have x2 is equal to y1, and y2 and z2 will be the same. After this, you have you know, y3 to denote timestamp 3. Okay, so here is saying y3 is equal to x2, and the other two will be the same. Yeah?
Why is it x2, sir? Shouldn't y3 be equal to z2?
Ah, correct. Okay, that's also a mistake. Y3 should be equal to z2, and z3 and x3 will be the same. See, an optimization, an obvious optimization, you must have seen, okay? It is not necessary to introduce new times. I mean, you need to update the timestamps only for those variables that are modified, correct? Okay, so then you don't need to keep all these extra things in here. Okay, an optimization is that you will only introduce new timestamps for the variables, only for those variables that are changed, okay, in a particular thing. And that is an optimization that you could use. And then you can have only z1 is equal to x naught, okay, and not use x1 and y1. But here you will use, since this is modifying x, you will use x2 here, okay, x1 here, okay, and leave the other timestamps. But you know, to make it simple, I have introduced a new timestamp regardless of whether the thing is changed or not. Okay, so that's an optimization that you can actually do, and that's what this single static assignment does. Okay, I think it's called single static assignment. Sorry, it's not static single assignment, single static assignment. That is what this thing is called, where you will introduce a new timestamp only to those variables that are modified in each of these statements. Okay. Then you take the conjunction of all these piecewise SSAs. Okay, and that is your model. That is the formula that actually models your program behavior in the sense that it captures any satisfying instance of the formula will precisely denote one execution for one input, okay, of that thing. Correct?
Yeah.
Okay. So given this, and it's in that sense that I saw the model, okay, the formula that denotes the program behavior is just a conjunction, just like the phi DNN, the phi corresponding to this program is just a conjunction of these formulas. And now here in the theory of inequalities over reals. Okay. So given that, in order to verify then this pre and post, what is it that you will have to do? What you will have to do is, given a precondition, that assuming that your initial values satisfy the precondition, the pre-predicate, and your program behaves as per the model that is constructed here as a formula in the logic, then assuming the precondition and your model, which exactly captures the behavior of the program for all possible inputs, then your post condition is always met. So the problem of checking that this program meets this pre-post condition for all possible input values for all possible behaviors is reduced to one of checking the validity of this formula. Okay, which really consists of pre-instantiated to the initial variables and the formula which denotes phi and then phi corresponding that the formula that denotes the model implies the post condition instantiated, the post predicate instantiated on the latest time-stamped versions of the program variables. Okay, so now you see this one is definitely, although this here is a mixture of program constructs and formulas, once you extract this, now here this verification condition is strictly a well-formed formula in that theory, okay, in the predicate first order logic of that involving those theories. So now I can ship this to a SMT formula, SMT solver and check the validity. In order to check the validity, now I'll have to, usually you convert validity checking is converted into a unsatisfiability check by taking the negation of this formula and then checking the negation, okay, which consists of taking the conjunction of the preconditions and the negation of the post condition. Okay, here I have instantiated the pre and post as per these things. And if you check this and your SMT solver comes back and says, yes, unsat, then you have verified that your program meets your pre and post condition for all possible input values. Okay.
Yeah. So this pre and post are, you are given the functions, right? And then you
specification is something that has to be given by the user. Okay.
Okay.
But the model for a program, this derivation of this formula can be completely automated. Okay. Although I've shown it for this particular example, given for any programming language, given its construct and so on, so it can be completely automated. Okay, and the program verification tools, they actually do that. Okay, tools, they actually automate that. And what they do is they take a program has to be given as an input and a pre and post, which are actually something they're called assertions. Okay, you can put assertions at various points in the program, and what the tool, which at the back end usually uses an SMT solver, does is it automatically derives this verification conditions, which in turn involves first deriving the model of the thing as single static assignment. Okay, and that part can be done completely. The construction of this model as SSAs and the derivation of the verification conditions given the program and your pre and post can be completely automated. Okay, and then you can ship it off to an SMT solver, and you have an answer. And if it is a bug, your witness to the unsatisfiability check being violated will be a witness to the bug. because it gives you exactly the violating instance, the model, okay, that is returned by the SMT solver will give you exactly the input for which the program violates the given pre and post. Okay, so any questions?
No, sir, it's clear.
Okay, so I told you that this thing is, this verification, the model can be derived automatically. Of course, I have only shown you for straight line program, not even branching program. How do you do for branching? Consider here a program which computes the max of two given numbers and assigns it to z. Okay. So one possible pre and post for this can be if x is less than y, then post condition z must be equal to x. No, it's the other way around, correct? Should be y, sorry. Huh? Correct.
I didn't understand, sir. What were you saying is wrong?
No. Okay, so I'll test your this thing. Does this program satisfy this pre and post condition?
Oh, no, it doesn't satisfy.
It does not. So that's
Yeah.
It should be y. Okay.
Yeah.
So this should be y. Made mistakes here. So consider this is y. So I'm going to show you exactly how the model, that this can be modeled as a formula involving a bunch of SSAs. Okay. Start with the initial values for x0, y0, and z0. So now here there is a condition. Here there is kind of two, there's a branching and there are two parts and then there is a merge after the if then else. Okay, so you need to kind of take care of that. Okay, so if x is less than y, then you assign y to z. Okay, so this can be this behavior of this side of the if then else, the conditional statement can be modeled using this implication. If x0 is less than y0, then z1, which is the value that is that defines the value that of the variable z after this assignment should be y0, correct? That is what is something that goes to there. Else, and the else part is if that is the negation of that is true, then you introduce a new variable which defines the value that z takes after if the control takes the else path and you reach this point. Of course, after that, your program, those two paths are actually, those two control paths are merged into a single point, which is at the exit of your program. So you have to define what the combined value is at the point where the two parts of the if then else are merged. For that, I use this conjunction. So I can either, this point after the thing, the merge point, is reached either by taking the if then part or the else part, right? So it says if x0 is less than y0, then z3, which is the merge point, the value of the variable z3 is equal to z1. Else, z3 is equal to z2. That is, if the negation of that condition holds good, then it is z2. So then now a conjunction of all these things. This piecewise, each of these is what I call as an SSA. Okay, this is a merged SSA, okay, that defines the value at the merge point. then your
Could you just explain again the third SSA? I didn't understand why it is there.
yeah. So you should imagine that this is so. So I want to define, okay, this Z1 I'm using the logical variable to denote whatever the value of Z is at this point, at the point, if you took the then part, that you agree, no?
Yeah.
Okay. Now here I want to define, I want Z3. I want to define, I'm introducing a new variable Z3, okay, because what would be the value of Z3 when you get out of the if then else? That is the point here, when you come here after the else, okay? So when you're done executing this, and you come here, okay, at this point, I'm defining Z3. So Z3 could either be Z1 or Z2, correct? If I taken this part, x naught less than y naught, then Z3 would be the same as Z1. Z3 is denoting kind of the value after you after executing both the possible paths that you could have taken in the two branches, then and the else branch. So if I so suppose Z3 is the value. I'm trying to define the value of Z3 after I execute the if then else statement. Okay, what would that be? It would be the same as Z1 if x naught was less than y naught. It would be the same as Z2 if the negation was true. That's all that thing is saying.
Yeah, sir. It's clear now.
So this SSA was a partial specification. It only captured the behavior corresponding to the then part. Okay, this and the precondition and the precondition here, because this path is going to be traversed, that this assignment Z is equal to Y is going to happen only if this the condition of the if is true. This would be executed only if the negation of the condition is true. Okay, so here I'm saying, hey, look, Z3 should be the same as Z1 if I take them the Z1, the then path, which is the case when x naught is less than 1. Okay, so that's all. So then if I take the conjunction of all these three things, and that is the behavior. Okay, so now you could then construct the verification condition just like before. I have not shown it. Okay, so assuming this formula is 5, that is the conjunction of these three formulas, this, and this. Okay, 3 of that is x naught, y naught, x naught less than y naught, and the conjunction of these three things implies Z3. Okay, you have to instantiate the post condition on the latest timestamps version for that thing. So you would have something, like this. If I were rewriting, so I would say, assuming that denotes this. So x naught less than y naught and 5, where 5 denotes this conjunction of these three formulas that I've shown here. Okay. And I take the negation. instantiate the post condition, negation of the post condition, okay, which is the negation of Z3, that is the timestamp thing, Z3 is equal to Y naught, okay? This should be the unsat of this. So pre and phi implies post. That is the validity check, which is equivalent, which is the negation of that is pre and phi, and the negation of the post condition instantiated on the latest, the variables with the latest timestamp. So here I'm not, I've used that optimization. I'm not incremented the timestamps for Y and X because they never changed. Okay, so Y naught and X naught are the latest time-stamped version of those variables. So the time-stamped version are the logical variables. So the program variables are the just without the timestamps. Okay, is that clear?
Yes, sir.
So that's what you do for branching, and you can see that even for arbitrarily nested if analysis, you can derive this formula phi corresponding to a program automatically. That's what for moments. So all the formulas, all the verification condition, the specification, everything is now within the first order logic of linear inequalities over the reals. Okay, and that is decidable. And actually, linear, the theory of linear, the conjunctive theory of linear inequalities over reals is polynomial in complexity. Okay, it is quite efficient. Yeah. So how do I deal with loops? So for example, for this program, this pre and this satisfies this pre and post. Suppose I start this program with X is equal to Y. After I execute this, no matter how many times, if Y is even, X remains even, correct?
Yes.
So this could be something, I mean, so it's a, there are various other properties that you can actually specify, okay? I mean, yeah, so I'm just giving you an example of a property. I mean, this is not a complete specification, but you can specify it completely or, various things. So this is what program verification is all about. You can specify various interesting properties about a thing and then use a verification tool. All such program verification tools have an SMT or a SAT solver at their back end. Okay, the front end, all it does is it derives these verification conditions automatically given the program and your pre and post. Now, the most challenging part is how do you have a loop? Okay, so there are two approaches that I'm going to be discussing. One is kind of an incomplete approach, not a very efficient, but an incomplete approach, but yet it is useful in practice for debugging, and a more complete approach, okay, which I will talk in the next class. One is to unwind the program up to a certain depth. Okay, so for example, this program can be unwound and represented like this. So say for 3 unwindings, we can represent it as straight line branching programs. Correct? Not If X is, then I exit, okay? So, and then you can check this for each iteration, okay? Because once you unwind, your program does not have any loops for that particular unwinding. And you could use the previous method that I showed you to derive the verification condition given the pre and post. But of course, for each for each unwinding, it says, okay, it checks that. Okay, it's a partial verification, not a complete verification. But maybe it's still useful. That is one way to do it. Okay. If you want to do it in a more complete way, there is this concept called loop invariance. Okay. And that's what I will talk about. Just like pre and post is a specification that you have to specify, the user has to give. There is some help that is required from the user, some hint, you could say a hint that is given that hint the user gives, then loops can be verified in a complete fashion. And for that, you need the concept of loop invariance, okay? And I will introduce that in the next class. All these things, these concepts, okay? There are, okay, the takeaway today, okay, so that's, I will do next time, okay? The takeaway today is the various things, how you could model these things, how the problem can be reduced to a problem of checking validity or unsatisfiability in a given, first order logic with over certain theories, okay? That is the takeaway that you have to to understand. Okay. Yeah. So any questions? I want to stop here. Yeah.
No, sir. No question.
Okay. Okay, then. Yeah. Good. So I will upload this, and hopefully other people will also have the thing, because the first assignment will be on some of these things that I've discussed. For you to do it and then try Z3 on that. So I'm going to stop sharing.